morning, everyone, and good evening to you, Philip, from Switzerland. So really nice to see everyone here, and today we're going to give a workshop on the QSDsan platform, which is our open source tools for the quantitative sustainable design and decision making of sanitation and resource recovery systems. Before I get started, I just want to say thank you to all the amazing folks at the guest group at the University of Illinois Urbana-Champaign. And so we're gonna have 4 main presenters here. So we're gonna each introduce ourselves. So I'm Yalin, and I'm the lead developer of QSDsan, oversee the overarching structure of the platform. And then I will hand to Joy.
Hi, I'm Joy. I'm a co-developer of QSDsan. I'm mainly in charge of the developing of modules for process modeling and dynamic simulation. I'm handed to Hannah.
Hi, I'm Hannah. I am a PhD student in environmental engineering, and I have been mainly involved in the DMsan package, which is the decision-making side of the sanitation resource recovery, and then also involved in creating the YouTube video demos. And then now Tori.
Hi, I'm Tori Morgan. I'm a postdoc in the guest lab group in environmental engineering, and I've been helping Hannah, Joy, and Yalin with developing the DMsan platform as well, and I've also helped with create some of the videos for QSDsan.
All right, and then so we'll go to the next step, which is one of the key steps for today's experience. So we're going to make this an interactive experience. To do this, please first log on to mybinder.org. So just type this web address into a browser, and then you should be looking at, let me do this as I type. So mybinder.org. After you log on, you should be seeing some screen like this. And then in this GitHub, you put in QSDsan-QSDsan-workshop, the first box. And then in this git ref, you put in main. All right. And then you click on this launch. You might see something like this. And then as you do, it should be lead to this page. And then depending on your internet and everything, it may take some time for you to open this page, but this should be like where we build this like remote environment for you to run Python remotely. All right. So if you see this, you want to double click on this example_interactive, and then it will open a new workbook in this window. All right. So this would be what our interactive module, which is at the later part of this workshop, we focus on. So we just want to make sure you can open this page, because sometimes this can take some time. All right. So if you are seeing some like blank screen, if you if on the previous page you see it's like it's not already built, it's like a still building or something, you just leave it as it is, and we will and then it will load itself. So hopefully you can get loaded when we hit this interactive module. All right. And now we are back to the slides. All right. So for today, we have 3 main sections. So in the first section, we'll go, so Hannah will lead this first section, and she will go through the examples we prepared for this workshop. And in this second part, so Joy will lead these discussions on the quantitative sustainable design, and then the how we can use QSDsan to design the system, do techno-economic analysis and life cycle assessment with under uncertainty, so with uncertainty and sensitivity analysis. And then Tori will lead the discussions on how we can do the multi-criteria decision analysis, MCDA. And then so I'll lead the final part, which is the discussion about QSDsan, DMsan, and together we run this live demo. All right. So now I will hand to Hannah, and she will go through the first slide.
Thank you, Yalin. Yes, so today I will go through the example that we're going to be doing for this tutorial. And so we are focusing on a sanitation system. And so just for some background of why we focused on this for the tutorial, up to 70% of sanitation systems in resource-limited contexts fail within the first 2 years. And so in order to meet sanitation goals, we need to make sure that these failures don't happen. And so some reasons why these failures might happen, a lot of times developers focus on silver bullet solutions, which means that you're choosing one technology and trying to fit it into every single context, which we know from experience that that doesn't necessarily mean that it will be a successful solution. Also, not adequately addressing the local context. So if we are using silver bullet solutions, we might not be thinking about the features of a context that would make you choose one alternative over another. And then maybe we have a great solution, but once we've installed it, we're not really thinking about what the operation and maintenance is required to maintain that system. And then additionally, there could be user interface complexities. So some systems might require a more complex toilet, and users might not have any familiarity with that. Additionally, there could be inconsistencies in how we make the decision. And so that kind of plays into the multi-criteria decision analysis component that Tori will talk about. And then also potentially excluding relevant stakeholders that might help you make a better decision. And lots of other reasons why systems could fail. And then, so big picture, when sanitation systems fail, we are not able to make progress towards achieving adequate and equitable sanitation and hygiene for all, which is the focus of Sustainable Development Goal 6. And so at the end of 2020, 3.6 billion, a little less than half of the world's population still lacked safely managed sanitation. 44% of household wastewater is not safely treated. And then on the decision-making side, only 14 out of 109 countries report having high levels of participation by communities in water and sanitation decision-making. And so with all of these statistics, we can see that there's a lot of work still left to be done in this space. And then specifically for this workshop, we are going to focus on a scenario in Uganda. And so currently in Uganda, well, not currently, at the end of 2018, 72 or 79.2% of the population was not using safely managed sanitation. So a huge proportion of the population is not having their sanitation safely treated and disposed of. And so for this workshop, we are going to focus on evaluating two different sanitation systems. Both systems have pros and cons of their use, and so we'll be able to evaluate which system makes the most sense for in Uganda, but also looking at other contexts too. And so the first scenario, system A, will focus on using a pit latrine. And so this is a more conventional toilet that is used widely in Uganda. Some of our group members had the opportunity to actually travel to Kampala, Uganda in 2018 to do some research there. And these pictures are not from that trip, just Google, but specifically for the pit latrine, all of the excreta is mixed together in one pit. And that is good to know because the other alternative separates them. And so for the pit latrine, a benefit is that it is widely used throughout the community. So people understand how to use these, what operation maintenance is required. A big pro as far as like the longevity of people using this toilet. It's also very simple and potentially less expensive than the alternative. Some limitations is that the pit itself could potentially lead to leaching of wastewater into the environment. It can be prone to collapse depending on the groundwater and soil conditions. And then if you're interested in recovering resources, specifically nutrients from the waste, having the waste solids and liquids combined together could potentially reduce the efficiency of your resource recovery. And then on the other side, so system B, we're considering a urine diverting dry toilet, which essentially allows us to separate the urine from the feces. And so that is a huge benefit if you're interested in recovering nutrient dense urine for resource recovery. And then it's also container based, so you could potentially have less environmental contamination related to leaching from the pit. And then a limitation is that it might not be as widely used throughout the community. And so as you can see, there are 2 separate holes for actually using it. And so some community members might not have any kind of experience with using this type of setup. So that would definitely require a little bit more education and helping people understand how to use it. And then this setup could be more expensive on just the construction of the actual toilet, but also, since it is container based, additional requirements in emptying those containers. Okay, so now that we have introduced those 2 different toilets, we are going to do a little bit of an exercise to get you guys thinking about this project. And so imagine that you're in a room of representatives discussing the next big community project to improve the sanitation access in Kampala, Uganda. And so this map shows where Uganda is in Africa. And then the yellow star is where the capital city, Kampala, is. And then for this example, we're just going to assume the population we want to provide sanitation for is 20,000 users. The whole city of Kampala is much larger than that, but we're just looking at a small neighborhood. And so just think about, if you are a representative thinking about what system you want, what kind of things would you care about? So if you're trying to make this decision, what decision-making criteria you want to consider, what types of people should you involve, just anything that you think would be relevant to the project. And so we are going to create a word cloud. This one? Yes. Okay, so if you go to LiveCloud Online, livecloud.online/join, you can type in this 4-digit code and then think about what things you think are important to choosing a pit latrine versus a urine diverting dry toilet. And you can add as many words as you want, and it'll populate this word cloud. So we have cost, definitely very important. livecloud.online/join.
Yeah.
But I think you want to have it /join, and then you'll type in TSJF at the bottom. Okay, we have environmental impact, user acceptability, O&M complexity, reliability, lots of really great things. Safety. Oh, coming in fast. Climate adaptability. Ease of use, yes. And if you agree with any of these, you can also type in the word again, and then it'll make that word bigger if you think one of these topics is more important than the others. Cost. Definitely hard to have a project be successful if it's too expensive for the community. We have a capital C cost and a lowercase c cost. We have community concerns. I don't remember if that. So yeah, lots of economics, environmental issues, community related, reliability, culture, definitely important. Yeah, think about, you're in Uganda, any kind of things that are relevant to that space versus if you're creating a project in the US. Odor. Okay, yes, so all of those were really good answers for the first question. We'll definitely get into more detail of what kinds of features we included in both this tutorial, but also in our packages as a whole. So now we will talk about specifically what is important to when you're designing these projects for a specific community compared to another place. So if you're thinking about both the technical design, trying to evaluate the costs of a system, the environmental impacts, social characteristics, what kind of parameters do you think are important to vary? Like what parameters would change when you're changing locations? So I can give an example, or we have an example, material costs, yes. So if you're thinking about the cost of a system, the price of concrete could be one price in one country, very affordable, but it might be very expensive in another country. So if your project is really concrete reliant, then that might change the economics of the system. We also have electricity costs. So if your project relies a lot on electricity, then it might be cheaper in one country that has low costs versus more expensive in a country that has high electricity costs. Yes, this person knows everything. Electricity, greenhouse gas intensity. Yes, so specifically what energy source your electricity is coming from. So if it's a low, or if it's a more renewable energy source, then you might have less emissions compared to a fossil fuel source. The topography of the location, definitely important. User preference, yes. Population density. Some systems might be better suited for a very densely populated location versus a spread out. The climate, the local diet. Waste content. All right. Yeah, these are all really good things to think about. Okay. We will definitely go into this in more detail for the actual tutorial. Okay, so that is kind of the brief overview of what we're going to be talking about. So before we go into the actual details of the methods, we just wanted to allow people to ask any questions or clarifying questions. So does anyone have any questions before we move forward? I can't see the chat, so I don't know.
I can.
Okay, perfect. And yeah, if you, especially the people on Zoom, if you have questions throughout, feel free to ask them in the chat and we'll make sure that we get those answered. Okay, so we've gone through the workshop example. So now we'll go through the detailed methodologies of how we actually assess the sustainability of different sanitation systems.
Thanks, Hannah. In this section, I will talk about the methodologies we use to evaluate or compare different technology alternatives. Imagine, for example, we have a system, we have a models for the two toilet alternatives, and we've already seen, we care about costs, we care about environmental impacts, and for those things, we want to be able to quantitatively evaluate them so that we can make a reasonable comparison between different alternatives. The methodology I'm introducing here is called Quantitative Sustainable Design. And this is the framework we will use to evaluate the system. Specifically, we will use techno-economic analysis to evaluate the financial viability of this project. And we will use life cycle assessment to evaluate the environmental impacts associated with different alternatives so that we can make a quantitative comparison and make an informed decision when we're choosing a specific technology for a specific context. And we also know that when we vary the context or when we evaluate the systems, there could be a lot of uncertainties involved, or the uncertainties associated with the system itself could affect how we choose the system. And we want to be able to, a good comparison should be able to take that uncertainty into account. So we will also introduce tool methods to help us first quantify what are the uncertainties associated with the input and the resulting uncertainty in the indicators of interest. And second, we want to be able to use these information and identify what are the driving factors of a project's financial viability and environmental impacts. And these methods are called uncertainty analysis and sensitivity analysis. And I will go over these step by step. First, to evaluate the financial viability, we use TEA, like I said, and TEA needs to take into account the cash flows along the entire life cycle of the project. We first identify what are the incomes and costs at each time point of the project. And for example, for incomes, for a toilet system, you can maybe charge users to use the system, and we will get user fees for that. And if the system is able to recover nutrients, for example, as to offset commercial fertilizers, that could also be another source of income. We could also get subsidies from the government, or if this system is in the carbon trade market, carbon credit is also another potential source of income. For costs, along the life cycle, we often consider them, at the start of the project, we have capital investments. This could usually include material cost for the system, land purchase cost, and along the life cycle of the project, we have costs associated with operation and maintenance. For example, the energy use, the labor cost associated with the maintenance and operation, and also if this project has some sort of income, it might get taxed. For example, for our 2 toilet systems, for the pilot train system, we will consider the materials, operation and maintenance of the toilet itself, also the transportation of the waste from the pilot train as well. And for the urine diverted dry toilets, we're also considering materials associated with the construction, operation and maintenance, and transportation. But the transportation will also include hand parts because it's a more complex structure. You can't just use cars or trucks to suck the waste out of the toilet. So we have one more steps in between. But we're not, for this specific example, we're not considering the end of life yet, but it's always an option. And another very important aspect of TEA is to take into account the value of time. For example, $100 in 10 years may worth only $80 now. And to evaluate the present value of a project so that we can compare them, it's important to take into account the discounting of money. And to do that, we consider discount rate, and we, depending on when the cash flow occurs, we calculate a present value of that cash flow, and we add them up so that we can estimate the net present value by subtracting cost from incomes. And this, because they're on the same time scale, we can compare, okay, if a project has a lower net present value than the other one, then maybe it's less financially viable than the other one. So similarly, when we try to compare environmental sustainability of a project, we consider materials and energy flows across the life cycle of the project as well. For our system, for example, we consider construction materials. Concrete, steel, PVC pipes are common ones, and what are the life cycle impacts associated with them, which includes not only using them, but also the manufacturing of those materials. And for the operation and maintenance, we'll use electricity, which has environmental impacts associated with them. A most commonly discussed one is the carbon footprint or the global warming potential associated with electricity. And for transportation, it would be similar too. But we could also consider the direct emissions from the system that has direct environmental impacts, such as the nutrients leaked from the system could have potentially negative impacts on the local water body quality. And for during the operation, there could be methane, nitrous oxide, which are important greenhouse gases to consider. And like I said, if this system is able to recover nutrients and sell it for fertilizer, it, in a sense, reduce the use of more energy intensive commercial fertilizers made from, for example, made through more traditional manufacturing ways. And once we have the items, we can, through different environment impact assessment methods, take into account, for example, for global warming potential, what's the carbon intensity associated with each item, and calculate a total global warming potential associated with different toilet alternatives. Similarly, depends on what kind of impact assessment method you choose. We can also assess eutrophication potential, ozone depletion, fossil fuel use, freshwater use, etc. So that we can have a direct comparison between the two alternatives. What are the environmental impacts? Now that we have the TA and LCA model, we want to take into account the uncertainties. And to do that, we need to, describe what are the uncertainties associated with inputs to the model, which could be uncertainties from the technology side, the performance uncertainties, or it could be uncertainty associated with the context, such as electricity price we just discussed. And through Monte Carlo simulation, and once we sample those uncertainty and put it into Monte Carlo simulation, we'll be able to get a distribution of the indicators of interest rather than just a single point value, which gives us a better sense of what are the trade-offs or what's a reasonable expectation for the performance of this system. And once we have these simulation data, we can make use of it and help us identify if we want to make a system or one alternative more favorable in a certain context, what we should focus on. Or if we want to eliminate or have a more predictable performance of the system, what are the main source of uncertainty we should try to reduce? And one example of such analysis is correlation analysis. Basically, we use the simulation data of the indicator and the input variables and do a correlation analysis. A larger correlation between them usually indicates that this input parameter is more important for this indicator than others. And another example is variance-based analysis, which basically attributes the variance of output indicators to different sources of input uncertainty. And this gives us a quantitative proportion of the output uncertainty to different sources so that we can make, we can focus on the biggest sources of uncertainty and try to work around it, either to improve the technology or to find a better context of deployment for this technology. And to wrap up, all these analyses I just discussed are available and can be easily implemented with the QSDsan package. We will have the live demo later. And now before I pass it to Tori to talk about multi-criteria decision-making, I just want to have a round of check-in and see if you guys have any questions about what I just introduced. Thanks for the applause, yes. All right, cool. Let's welcome Tori.
Thank you, Joy. Nice job. So I'll be talking about multi-criteria decision analysis, and what that is, it's a type of analysis that's used to evaluate multiple conflicting criteria in decision-making. And so the first thing you want to do is define the objective of your MCDA. So what are we trying to do? And so it could be to choose, could you click, sorry. It could be maybe you're trying to choose your best career and you have all these factors that you're considering. How do you do that? Or choose the best location to live in, or choose the best location to deploy a technology. And the example that we're going to go through, we're going to choose the best technology for a specific location with the technologies that Hannah mentioned prior. So once you have your objective, then you need to think about all the factors that go into your decision, and these are known as criteria. So for choosing a sanitation technology, one criteria could be the technological resilience of the technology. So how does it perform in different climate conditions or with different population growth rates, and anything that could impact the technology succeeding or failing. Another one could be the environmental impacts, like some of the ones that Joy mentioned in the LCA discussion. And then we can look at resource recovery. Is there one technology that recovers a specific resource better than another? Or is there a technology that recovers multiple resources in the technology? And then as we saw in the first question that Hannah proposed is, what is something that really influences technology adoption? And that's cost. And so we can look at the economic impacts of each technology. And then finally, a lot of people mention, cultural factors, social factors. Well, we can look at the social impacts that each technology has for a given location. For simplicity and time's sake today, we're just going to go over the criteria of environmental impacts and economic impacts and see how that can impact our decision. So then once we've defined the criteria that we want to use, we have to weigh the criteria. And so it could be maybe you care more about the environment or you care more about the economic. For this example, we're going to say that we value both criteria evenly. So we're going to give a 50% weight to environmental impacts, and we're going to give a 50% weight to economic impacts. So you just want to make sure that whatever your criteria are, that all the weights equal to 100%. And then Hannah mentioned the technology options that we're looking at. So we have a pit latrine and the urine diverting dry toilet are the alternatives or options that we have for the location in Kampala, Uganda. And then finally, we want to rate how these technologies perform. And you want to make sure that this is a normalized score. So we're going to look at a score of 1 to 7 and normalize it to that scale where 1 is the worst and 7 is the best that you can give a technology. And so for environmental impacts, we have a 3 for the pit latrine. And that's because we're considering that, it's not recovering any resources, or maybe it has more methane emissions. And so it'll get a lower score compared to a urine diverting dry toilet that might have less emissions and better resource recovery. And then the pit latrine might be more economic compared to the urine diverting dry toilet, either in the short run or the long run, depending on what the stakeholder that's going through this analysis cares about. So then how we'll calculate each one is you take the score and multiply it by the weight for that category or that criteria. And then you will do a sum of the score multiplied by the weight for that technology. So we can see that the pit latrine got a score of 5 and the urine diverting dry toilet has a score of 5.5. So it barely won, and we would rank the urine diverting dry toilet as first and the pit latrine as second. But this could change depending on what weights you give to the criteria, or maybe you have sub-criteria that are involved with the main criteria, and so that could also impact your score. So that was a very brief overview of multi-criteria decision analysis. And this is kind of what we use for the decision-making sanitation package DMsan. So are there any questions just about MCDA so far? Okay, if not, I think we can move on.
All right, thanks, Tori. All right, now we are getting to the final part, which is about the tools. So the tools, QSDsan, DMsan, and also a live demo. All right, so I'll give a really quick overview of what the tools looks like, and then we'll hit this live demo module, which I think will be fun. All right, so we have 2 tools here. So first is QSDsan. So as Joy talked about, and as name implicates, so this QSDsan, it takes care of from the design of the system. For example, we have to design this, like if we want to know the cost or environmental impacts associated with the system, we need to design. We need to have a system first. So it takes care of from this design simulation to this T and LC process under uncertainty. So QSDsan actually uses a lot of the different open source packages that our group developed to for rigorous and automated simulation. So at the bottom part, so here you have several classes in QSDsan. So class is just a concept in Python that you can think is a group of objects. So we have classes in QSDsan that is inherited from that follows apart from the thermal steam, which is packaged that I already remember, to do this thermodynamic simulation. And then we have this process class that's unique to QSDsan that takes care of the kinetic modeling. So if we are thinking of designing a more complicated systems with dynamics, with kinetic rate equations, etc., so this class will be very helpful to you. And then we have several classes there that takes care of the design of the unit and then the different combination of the units into the system, and then help you to do this TA analysis, and that is sort of from BioSteam, which is the open source package that's designed by that's developed by our group. That gives QSDsan ability to design simulation TA. And then we have several classes and QSDsan takes care of the LSA. And I want to emphasize that although the example you see later, we are focusing on the global warming potential, so GWP, but actually the QSDsan we can take care of a bunch of different indicators. So whatever you like, whatever life cycle inventory assessment method you like. So we can do that in QSDsan. And then finally, so we talked before that, like, if we are thinking of simulating a system at different locations across this world, so there will be a lot of contextual parameters that varies based on where this technology is deployed. And then to take care of that, we have this DMsan, which is for decision-making part. So that gives, first, it has a database related to the contextual parameters that is particularly relevant if you are thinking of sanitation technologies. For example, we have database on the price of fertilizer. We have database on the diet of the typical residence diet intake at a certain country. And then DMsan also, in addition to this database, I also have a bunch of different methods to do this multi-criteria decision making. So what we covered before, like when we are talking about, like, we are looking at these 5 criteria. So what Tori didn't mention is that we actually, for each of those criteria, we might have a lot of different indicators. For example, if we are thinking of like the social part, so that could be like depending on like people, whether people value their like privacy, like whether people will think about like how far away is this toilet from their their home. So like all of those will actually come into play in the DMsan package. But for this example, really for the simplicity, we will focusing on the economic and environmental part. All right, so that's a quick overview of all the packages. I know I can overwhelm you, but hopefully this will become clear as we go to that interactive module. And you are always welcome to ask later for questions if you are really interested in to learn about the details of our packages. All right, and also, so if you want to learn more, what you can do is to just do this Google search, or you can just put it in this web address. So what it leads you is click on this. It will give you to the GitHub homepage of QSDsan, and we have different badges here. So all of the badges, they mean something. So this one, it will lead you to the documentation part of the QSDsan. If I click here, you'll see this page, so which has all of the information on like what is QSDsan, how does it work. And then if we'll click on the left part, so under this topical tutorial, you'll see a bunch of different tutorials, and Tori and Hannah, they did a really good job in recording the video tutorial. So if you did any of those, you will actually be able to see some video demo. And then like if you want to watch the a video demo, you can hit on this YouTube link. You will go to that YouTube link. And then, so we also, you see, here. So if we want launch QSDsan in an interactive module, as we will show later for this workshop, you can click on the badge. If you want to receive news about QSDsan, you can click here. It will actually lead you to a subscription page where you can subscribe to the newsletters. And then if you want to know, okay, what's going on in in the recent times for QSDsan, you will see this Google Calendar, and you can see right now we're at this workshop of QSDsan. So a lot of resources on the homepage of QSDsan's GitHub. So if you're interested, click on any of those later. But for today's demo, so we'll use this interactive module. So for the people who are new here, so if you want to go to this page, you can, in your web browser, I'm just repeating what we talked about earlier. So go to mybinder.org. All right. So in this GitHub box, type in QSDsan -group/QSDsan -workshop, and then on this git web, put in men. All right, and then hit on launch. So this may take some time, the first time to launch it. So for the people who joined earlier, I hope your page is already launched, but if not, you can try to do this again. See this beautiful thing. All right, since you haven't. All right, anyone has any problem in opening this page? All right, everyone has this page open? Awesome, cool. All right, it works better than I thought. I'm starting to believe in technology again. All right, okay, so we have a lot of modules here. Essentially, so what do you want to look at? So today we'll focus on this example interactive. All right, I'll double click on this one. But if you are interested in coding in like, oh, so look, how did you get to all the results you will show later, you can open this example _complete. It has all the code on the like behind this related to this example. If you are interested in the code of actual QSDsan or DMsan, it's on GitHub. You just Google it, or whatever like a search engine you like to just search for it. And then there's a bunch of Python modules here that basically has like the code for like, for example, this one, that's the context specific analysis. All right. So now we're on to this interactive module part. All right, so here's a table of content. If you want, you can click on that. And then I will go to two important instructions here. First one, to run a module in Jupyter, in this interactive environment, you need to select this module and then click this play button. So essentially this will run this, all right? And then the second part is that if you are doing something, for example, if I want to first look at the setup of the system, I click this run button. Let's see. If you say start here, it basically means it's running, all right? So just be a little bit patient and wait for it to turn into a number. All right, it can be a different number. This number just the order of the order that they will run the cells. This is the first cell I run, so it's order number 1. Okay, hit on this first block, hit run, and then second one, hit run. Okay, so what it will show you in this first block, it actually will show the system diagram for 2 different systems. Again, system A is the one with a pillar train. All right, so we have this pillar train. We have actually A1 is the first unit. So all the units, they are represented by a square box here. So all the yellow, sorry, not yellow, what I'm doing here. All these blue arrows here, they represent a string. So and then if you see like this arrow is also a string. All right. So you can see like starting from the first unit is called excretions. Essentially, that's basically someone use the toilet. All right, to put it in a nicer way. And then we have this pillar train, the second unit, and then it basically takes the urine and feces from this person or whatever uses this toilet, and then we'll go to this like transportation process. At the same time, because some of the organics may degrade during this in this pillar train, you will see this methane and then N2O emissions, and also there's leachate for this pillar train. And then after this transportation, we'll have these applications of this material of this excreta. And then we'll kind of the last part of this unit just a way for us to account for the different recovery of nitrogen, phosphorus, and potassium. And then there's some loss during this process. All right, so that's the first system. And then very similarly for system B, with only change here, mentioned here, is actually instead of that pillar train, we have this UDDT here. We still have the excretion unit. We still have this transportation, but right now, because UDDT separates the union from the feces, so now we have 2 different transportation units. We have this B3, which is for the liquid, and then we have the B4, which is for the solid. And then they go through pretty much the same, because we have the same assumptions for what happens after this product. All right, So that's the system diagram, the processes. Now let's go to the fun part where we can actually do T and LCA. So you can ignore all of the codes there. This is just to let you know that if you want to have something like this, this is you need to put in. But you just hit on the hit on the play button and play button. All right. Okay. So now you can select whatever you want. So like we have different metrics for TA. We have different metrics for LCA. I'm actually only displaying the most the simplest part here. For the TA metric, we have net cost, or we have capex, which is for the capital cost, opex for the operating sales. Essentially, if you like for the nutrient recovered from the excreta, so like how much we can get, how much we can get if we are selling this. And then for the LCA, similarly, we have the construction, we have the net, which is basically everything added up together. We have the construction and operating, and then the operating includes transportation, direct emissions that include the methane and N2O, and also we have offset from nutrient. So you can select whatever you want, however many you want. If you want to select multiple, you can either shift click. Oh, it won't work. Okay, you can command click, or if you're the Mac, or control click if you are using Windows. Can click different one and click on simulate. All right, so you should be able to see something like this, basically the results of the TLC of the metrics of the interest. For example, so here we can, so first one shows the cost. So for system A, the train system, we have a lower cost. It's about like 1.5 cents per capita per year. It's actually per day. I need to fix this. And then we have the capital, so that's net cost. We have capital cost and operating cost. The operating cost for the system B is high because so the UDT, because it's a containment-based system, is emptied at a basis of, at a frequency of about every 3 or 5 days. For the peak train, it's only emptied like once per year, or like maybe a little bit more frequent than once a year. So that's a really big difference in like the transportation. And then for the emissions here, so the net emission for the system B utility is actually negative because it will be able, because of the source separation, it will be able to recover much more nutrient than the peak train. So it has a higher offset, so that leads to a negative emission. All right, you can play around with different metrics if you're interested. You should be able to just select any others and then simulate should refresh. All right, everyone so far be able to run this example, no problem. Okay, cool. So that's TA, LCA still holding up. All right, so that's one part of the calculation done. And now let's hit the MCDA part. So 2 cells, and then you will be asked questions. So which TA metric you want to use for the economic criteria, and which LCA metric you want to use for the environmental criteria. So let's assume we just want to use the net here. So it's the net cost and then the net emission. So the plot you are looking here is actually simulated across this economic weight. So when Tori was talking about MCDA, she gave an example of 0.5 goes to the economic and 0.5 goes to the environmental, so 50%. Now you can actually look at, so what if I value economic more than environment? For example, if you as this like red side of this plot, you can see like with the increase of this economic weight, the performance scores or the final scores you calculated for the system A peak to train is higher than system B UDT. So this is because it makes sense because from TA we know that the UDT system B, this system costs more than the peak to train system. So if you give more weight to this economic side, it will go up. All right. So you can try some interesting other things. For example, we know that the construction part of the LCA, even for the LCA, for the UDT system, actually has more emissions because like the UDT system uses more materials and this material can be more energy or intensive. So if we choose net cost for the economic and then also construction for the environment, you can see actually there's no way for the UDT system to outrank the peak system at all. So you see this straight line basically means like every time they compare the peak system overranks or wins over the the utility system. All right. Everyone still holding up, still be able to run the example. All right. And then all of that, that's just under some baseline assumptions. And now what we want to do is to look at this system under uncertainty. So for all of this analysis, we actually for this system consider a lot of different parameters just for these units. If we change the value of these parameters, for example, if we change how many people use this solid, and then or if we change the price of the nitrogen or potassium fertilizers, that will consider to be like the equivalent part of the nutrient we recovered from the excreta. For all of these parameters, if we change any of those, it will affect results actually. So we will want to run uncertainty and sensitivity analysis to see what it looks like if we use different set of parameters. All right, so this part, that's just that. Again, similarly, now you get to choose how many samples you want to run here. So I won't advise a really big number for you to be able to get some results before launch. All right. So, but if you are doing this for research, I also won't advise for a really low number. So if you are really considering doing analysis like this, at least like the number of solutions you want to run depends on how many uncertain parameter you have in your model. So for this, we actually, for a system we construct, we actually use at least 100 or 1,000, at least 1,000. But for everyone to go to launch, I'll just type in 20 here. And then I have to add this because I know that we won't be so patient if we are not seeing this, something like this. Okay, all right, cool, we get the results. So you can select what metrics you want to show the uncertainty analysis results. All right. I will pick all the costs related here. Okay, and then you can see what metric you want to show for the sensitivity analysis. The sensitivity analysis we run here, that's a Spearman rank correlation. All right, I'll actually first show this, and then I will talk about what this results mean. Okay, so this is uncertainty results. This showing this in this box plot. Essentially, what is you can see here is like this line in the middle. That's like the median. So like all of the 20 ranks, like what's the median, and then so this edge of this box, I think that's the first and third quartile of the results. And then like the diamond scale are the outliers. But essentially the results here is like you can look at this median line here to know the kind of the median value, and then you can see you can based on the whiskers know like what's the range, like how big the range is. And then the first one for the cost is all on the basis of cent. So US cent per capita per day. I say this for this first system, and then for the second system. All right, and then the sensitivity analysis. So that's from the Spearman rank correlation. So if you will see some like a tornado plot here. So some values are positive, some are negative. So positive value means like this uncertain parameter has a positive correlation with the result, or the results has a positive correlation with this uncertain parameter. So the higher this parameter value is, the higher the metric or the value of the metric is. So this one for system A, I'm showing I'm doing this sensitivity analysis for the net emission. Okay, so you see the top, like the first one, it has, so this is the energy or the calorie a person the calorie in this excreta generated by a person. So like this, it has this parameter, it has a positive correlation with this net emission. That's because in the pillar trend, because of the really low emptying frequency, so a lot of the organic matters which generate from this person excreta get degrade over time. During this degradation, it generates methane, and that is really a big source of this greenhouse gas emissions taken account into this net emission. This means like the more the people eat, the more the people generate, and then because that's all like a lot of that gets degraded during this process, the more greenhouse gas this person generates. All right. And then that's the similar thing, and that's also for the system B. That's kind of interesting. So we have another case like the household size has a negative correlation with the results for system B. All right, system B, UDBT. So that system has a higher construction intensity, or it uses more material. So a lot of emission from that system actually from those materials. The larger the hot side is, it basically means more people are using this one toilet. You're building fewer toilets there. You're using fewer materials. So thus this lead to this lower net emission. All right. Okay, so that's kind of the results here. So I hope everyone was able to run this example, kind of understand all of this. Okay, no problem. All right. Now we get to this final analysis, which is country-specific analysis. So all of the analysis we talked about, we are thinking of like we are doing this analysis in Kampala, Uganda. But there's a lot of different countries in the world, and there might be specific set of parameters we want to look at to run this analysis. So what if this system we're looking at is at a different place? So we want to run this for different countries. All right. So we have two questions here. First one, would you like to use the database value? Let's assume we don't want to use this. Please enter a country name. So something from the audience, give me a country name. Brazil. Okay. All right. Okay. All right. So we have some data from database. Basically, this shows what we collect on, and then these are the parameters we consider for this analysis. We actually consider much more parameters in our typical analysis. But this is just again for the simplicity of the workshop. We also consider this caloric intake. How much intakes people get from vegetable protein intake all daily, and then animal, and then the price of the different fertilizers, and the food waste ratio is like how much food this person like waste, and then there's price level ratio is basically it's kind of like a relative ratio on like if the things are more expensive at this place, this price level ratio will be higher. So if it's lower, it's less expensive. Then there's also income tax. And then we can use this later, like economic weight in MCDA. Then simulate. All right, so here's the result. Essentially, it basically runs all of this and shows the results in the recovery of different nutrients or in fraction, and the cost, and then the emissions of this system. All right, and then you will see this final score. If we see like under this 0.84 of economic weight, with the system A, the train system outranks or outscores this system B, the UDT system. If we lower, our scores are kept unchanged, but you can see like the score for all of these on certain this recovery, cost, emission don't change, but this final score changes. If we want to put in some number here, you can try to put in some numbers here. For example, if we consider a crazy selling price of the national fertilizer for a hypothetical country, for example, for whatever reason, that country has no fertilizer at all. So fertilizer value is $70 per kilogram. And then, okay, so here's the data we want to use, $70 USD per kilogram. National, simulate. All right, so basically, obviously there's no score for system A at all, because system A won't be able to recover as much nitrogen, as much nutrients as the second system. Like it doesn't matter at all, like which like what kind of numbers I picked here for the economic. There's no way for the first system to win. Okay, that's the last example. So but this basically shows you the capacity of QSDsan together with DMsan. There's a lot of things we didn't really get time to cover here. One part question we get whenever we talk about LCA, it's just like, oh, but we need those inventory data. How we get those inventory data? So there's actually ways for you to, if you're using equal events, there's actually a little package we made to help you to retrieve data from equal event and then pass that into QSDsan and use this. And then like for the DMsan, just we really skip a lot of details. Like if with regard to considering different indicators within a global weight, within certain criteria, there's a lot of different ways for us kind of normalize the scores from different indicators across this. For example, DMsan that you kind of experienced here, but we didn't talk about is like the cost is in the unit of cent per capita per day. The emission is in the unit of gram CO2 per capita per day. We can't just compare those numbers. We need to do some normalization. So that part we didn't cover, but all of that, we have algorithms for that in DMsan for this decision making. So that's basically all the materials we prepared here. Again, like I said, if you are interested in this coding part, you want to know what goes behind all of this, you want to do the more fancy uncertainty and sensitivity analysis, you will find my examples in this complete Jupyter notebook, which it does require some of these Python skills for you to be able to run this analysis, if you are really interested. All right, with that, I will stop talking, and then if you have any questions from the audience, we are about 17 minutes early for the launch, and the launch is there on the grid, so we are really convenient. And I'm sorry for the remote guys, but still, I hope you had a fun experience here.